So in the last podcast, what we looked at was that Edwin Hubble actually expanded our view of the universe exponentially. It went from one universe, aka a galaxy at that time, of 100 billion stars or so, to billions of galaxies with hundreds of billions of stars in it. And that could have been enough, but actually there was even a cooler discovery that he made. So Edwin Hubble's universe beforehand was thought to be known as a steady-state universe. Now, what does a steady-state universe look like? It basically is what the name implies, that it is what it is and it never changes and it's always been there. So for one, it's infinitely old, that it is no beginnings, no ends, it's just going to keep doing whatever it's doing, and that it's infinitely large, that you can go out in any direction as far as you want, and there is no end. There's no edge to the universe. In other words, it's infinite in size. There is a cool paradox of this called Ober's paradox, and I'm going to have you guys actually go look at this after this podcast, but not right now. So that's the idea, that the universe is infinitely old and infinitely large, and we're going to see how Edwin Hubble actually changes that. So first off, quick review. This should look familiar from last unit. This is actually the absorption spectrum of hydrogen. Remember that the hydrogen atom gives off certain wavelengths of light, and they would be specifically at these points. And that's a fingerprint, so it doesn't change. Well, let's take a look at a different one. When we take a look at a distant galaxy, what we see is that it looks really similar to the hydrogen spectrum, but it's just been shifted a little bit. It's the same exact pattern, but not quite in the right spot. So here's the question: how in the world could that possibly happen? All right, so shift it to the red part. And whether or not you're aware of it, you have some understanding of this process already. We know this was made out of hydrogen, but the spectrum's off, and this is called the Doppler effect. Now, the Doppler effect is most noticed here when you hear a train go by, or if you've ever seen a very fast car moving by. What you actually hear is caused by the Doppler effect. So what you just heard there, hopefully, was that as the car was coming towards, it actually was a lower pitch, or excuse me, a higher pitch than when it went past. All right. That is an example of the Doppler effect, that the waves, as they are coming towards you, were crunched together, making it a higher pitch, and as the car passed us, was a lower pitch. Right. That's called the Doppler effect. It works for sound, but it also works for any waves, and light is a wave. So when we see distant galaxies, right, and we see that shifting, well, that's caused by motion. So, real quick, as a source of light is moving towards us, say this star, which is yellow, is moving towards us, we would actually see the colors shifted towards the blue. Right, so it wouldn't look yellow, it would actually look blue. It's called a blue shift. And that indicates something would be actually moving towards us. Just like that higher pitched sound, you would see a higher pitched light. If a source of light is actually moving away from us, all right, that yellow light would have its light stretched out, which would appear to be a lower energy, which is a red shift. Okay, so it would look more red. When we look at a star, again, we see this spectrum. If it's moving towards us, you can see that star is racing towards us, we would actually see those lines shifted towards the blue end of the spectrum. And if it was moving away from us, right, see that star appears to be moving farther away, those lines are shifted towards the red. And the faster that it's moving away from us, the more the shift. So when we look out at galaxies, we actually see, for example, the quartet here of galaxies. we would see several different spectrum. And we can see that this guy, which looks really small, has the greatest shift. This guy right here, not so much. This is the second fastest galaxy away because it's shifted not quite as much as the bottom one. But the red shift is actually relative to its velocity. It's moving faster away from us. This is the fastest, the second fastest, the third, and the fourth. And what Hubble did was he measured the distance to these and then plotted the recessional velocity against its distance from us. And when he did that, when he plotted out that recessional speed, right, along with the distance, what he saw is that the farther the the galaxy is away from us, the faster it's moving away, and it's moving away at a roughly proportional amount. So the question is, how fast is it moving compared to its distance? Right? We can actually use the slope of this line to, which is known as the Hubble Constant, to age the galaxy or the universe. How long has it been flying away from us? The big deal about this, all right, all galaxies are pretty much red-shifted. There's only a few that are blue-shifted, which means they're all moving away from us. The farther away they are from us, the faster they're moving away from us. And what the Hubble Space Telescope actually has used, or one of its main goals, was to measure this Hubble constant, and it came out to about 70 kilometers per second per megaparsec. In other words, the farther away it goes, there's a measurable amount that it's moving faster away from us. And how this changes the big paradigm is that the steady-state universe is false. Right? The universe is actually expanding. The farther away something is from us, the faster it's moving away. So the question is, if it's getting bigger, in fact, it's bigger now than it was when I first started talking and you started watching this, what happens if I start to rewind this video? All right, it would be a little bit smaller and smaller and smaller, so that eventually, if you kept rewinding time back and back and back, you would get to a point where all the galaxies in the universe and all the matter contract to a point in space. This is the basic idea of the Big Bang. We can see that the universe is getting bigger and bigger and bigger, which means if you go back in time, it gets smaller and smaller and smaller. So you run that out and it just comes to a point. All right. The universe is not infinite in its age. All right. And this actually will help explain Obler's paradox, which you'll watch again after this. But there's some really big questions about the Big Bang. When did this happen? All right. We think it was about 13.75 billion years ago. And the reason why we came up with this number is that the Hubble constant is actually an age. All right. It's technically an inverse, but you can cancel it out, and it comes out to 13.75 billion years. And there are a bunch of other questions. So if it's expanding, well, where's it expanding from? Is there a center? Is there, if it's not infinite in age, is there infinite in size? Or is there an edge to the universe? These are all really good questions, and there are some really good videos that I want you guys to watch to help guide you in your exploration of these questions.